robots can provide a continuum between fully supported training wheels, bike riding, and I don't know, like using mountain bikes in downhills, right? So there is a continuum that can be set by modulating control parameters. And this is what we do in our lab. We try to use robots to challenge individuals in an adaptive way. And so what we do is we develop assisted needed controllers that, based on measurements of functional recovery, can adjust treatment. And so we do that using algorithms, and I'm not going to describe them in the detail, but however, they are block diagrams that define what control actions to apply to robots. Here you have a model of a robot. And then how to adjust their residual contribution based on an estimate of how well the subject is doing. And so we have a video here that will describe what we do. So this is a video taken at Rice University a year ago when we were developing this upper arm exoskeleton. It's a 4 degrees of freedom robot, which means that it can assist elbow flexion extension and the 3 wrist rotations. And so you can see that the subject here is interacting, grasping a handle, and then moving its joint. And what he can see is a video game of what he's doing. So there is a cursor that will move across this via points, and so it will have to go up and then down, and using one joint at a time. And so how do we modulate challenge in this type of task? Well, we have an algorithm that distinguishes whether the subject is passive or active. And so in this case now the subject becomes active, and you can see that is like leading this ghost cursor that's behind him. And so here that's where the subject leads and is in front of the ghost cursor. And that's where instead the task goes into subject-defined timing. It's the subject that, based on his capability of controlling his movements, will decide how quickly and how accurately to reach a target. And so then the algorithm is always measuring for continued improvement in this motor task, and when it detects that the subject lags, for in this case, the system switches back to robot control movement. So this is a substantially different scheme of human-robot interaction than the one you've seen in the first slide, where humans were in cages and robots were on their own. And this controller has been clinically studied in a patient population. So in this case, we compared the outcome of therapy in 2 groups that underwent robotic therapy. One group would keep the challenge constant throughout therapy, and the other group would undergo this sophisticated assist-as-needed algorithm. And so these are the 2 groups we show here. The control group is shown in blue, and they did show some improvement in the outcome measure. In this case, it's the RAT scale. However, non-improvement was statistically significant. However, the group that underwent the adaptive training, although didn't improve significantly after therapy and after 2 weeks, showed greater retention of motor skills. So the first clinically significant improvement here is measured after 2 months of their visit and of their therapy program. So in my lab at the University of Delaware, we are currently trying to extend these findings from upper arm training to gait training. So this is an exoskeleton that's available in my lab at the University of Delaware. It's called the ALEX, Active Leg Exoskeleton. It's essentially attempting to have individuals whose gait pattern is described by this trajectory in the space of hip and knee, the plane, to essentially push to trajectories that are those of physiologic gait. So how do we do that based on real-time observation of gait impairment? That's what we are currently studying in my lab. However, I want to highlight another feature of the research that we do in our lab that's trying to go past the current paradigm. So we have demonstrated so far that robots can automate stroke rehabilitation. However, recovery has a high level of inter-subject variability, and there are a very wide set of variables that may be able to predict this variability. And so, of course, variability of outcomes will call for customized delivery of treatment, but how do we understand which treatment works for which type of stroke patient? So we go back to our block diagram here, and we see like this, the block diagram is based on a feedback loop, what we call a feedback loop, that measures recovery and then adjusts treatment, right? However, since there is an intermediate step here, can we formulate ways of adjusting treatment based on measurements of neuroplasticity of this intermediate block? So that's something that we have started to do in my lab and in my previous research experience by developing robots that can be used in conjunction with functional neuroimaging. Functional neuroimaging is done in magnetic resonance scanners, and so most of the materials you would use for standard robots you could not use. So we developed passive devices that can measure displacements via optic fiber sensors, and we replicate rehabilitation tasks that are done outside the scanner, in the scanner here, like shown in this schematic. So our first study tried to provide a response to this question. So can functional measures of brain activity that we measured before rehabilitation correlate or even predict subsequent recovery? So what we have done, we have involved subjects in, before their enrollment in the therapeutic program, we have involved some subjects and we have invited them to undergo a session of functional MRI in a scanner. And so what we do is we take what's called a resting state functional connectivity map that describes how brain areas are connected together. And then we repeat this resting state connectivity map after the subjects are exposed to a short dose of exposure to motor challenge as triggered by these reaching tasks. And so our research is motivated by observation that changes in functional connectivity in your brain is indeed associated and in a very short time span with motor learning. So what we asked is if these guys here showed that motor learning does modulate functional connectivity in these two areas, as shown by the difference in these two bars, can we show a similar difference in post-stroke and stroke subject that will then undergo a process of neurorehabilitation, and can that change predict recovery? So in our pilot study, we showed that there is support for this hypothesis. So we have the two subjects here that show differential response to therapy after 3 months of robot-aided therapy. And that response was predicted by the pre-therapy response to this intervention. So if this is true, then it means that we can understand which patients can benefit from a given intervention and then tailor our therapy to those needs. So to study this type of problems in detail and to be able to enroll a wider population to this experiments, we have developed the first MR-compatible, magnetic resonance compatible robot. It's called the soft wrist, MR soft wrist, because it measures and provides assistance to wrist movements during functional MRI. This is a type of experiment that supports, so this is a wrist circular arc pointing experiment, so you can see that there is a cursor moving in the screen and the subject, the target is blinking, and the goal of the subject is to reach the target by pursuing the circular trajectory without violating this tunnel constraint. So the goal is to be as accurate as possible. So we want to understand if, based on the response to a short amount of motor learning before enrolling patients to a therapy program, we can predict subsequent recovery. And so that's actually one of the studies where we are enrolling our subject. And the reason why we want to do that with a robot is that we can systematically, again, modulate motor challenge. And this is shown in this plot where we apply a paradigm called error augmentation. So if we measure that subjects are slightly off the nominal trajectory, we can apply forces that will amplify the error. So how do subjects learn to respond to such a perturbation? So this would be a training mode that would be beneficial for subjects that have recovered motor capabilities and now need to be engaged into progressively more complex and sophisticated fine skill learning tasks. So the first question we try to address here is, can we expose subjects in functional MRI to systematic motor learning? And so our first results show that that's possible. So these are the kinematics, so movements of subjects, when exposed to different control modes, and we will focus on this EA, shown in red, which is error augmentation. And the ZF is the zero force, which is when the robot is not opposing any perturbation force. So in this experiment, we show that the error provided by the red lines is much greater than the one intrinsic by subject that are here in the cyan areas. So we can modulate motor challenge with fMRI. The next question is, can we measure distinguishable neural response? And so via fMRI, we can, for example, see that the error augmentation paradigm provides a greater response from brain areas that are associated with motor learning and compensation for task errors. So that's the area where the motor control feedback controller lies. And this is in fact the contralateral to movement cerebellum. Okay, I want to leave time with some questions, just to finish with an overview of some of the research activities that we do in my lab at the University of Delaware. So our research is split into two areas. One is really basic motor control research. So as I said, we want to modulate challenge via robots using sensory motor tasks. And can we distinguish between the neural representation of different tasks, which means of different controllers that promote neurorehabilitation? So then another area of research is like motor control is, of course, not only brain. We use neuromuscular models and to understand how subjects learn to control many muscles for complex manipulation tasks. So finally, a big part of what we do is actually rehabilitation research. We try to respond questions such as, can we teach new locomotor patterns by applying these subject-specific pulses of toward the exoskeleton? And can we use functional neuroimaging and specifically short-term neural reorganization to predict outcomes of robot-aided rehabilitation? So with that, I would like just to show a picture of us, the Neurolab, and to acknowledge the work of my students who have been working on some of these areas. We are located at the New Star campus here at the University of Delaware. And with that, I would like to acknowledge some funding sources and to, if there is time, respond to some questions. Thank you.